morning, good evening, wherever it is for you. We will be doing systems of linear equations these next couple videos. Today we're going to focus on when we have a system of equations and we only have two variables. Tomorrow we'll get into three variables. Apologize for my voice. It's not coming across clear. I have been pretty sick, but I'll do the best I can as far as my volume goes. So first off, we need some definitions. What are we going to be looking at? A system of linear equations is going to consist of two or more linear equations. I want to focus on that word linear, okay? Meaning that my x is just going to be x to the first power. My y is going to be y to the first power. No square roots, no powers. We're going to leave it basic for now, okay? And what we're going to be doing is we're going to be taking equations that involve x and y, and we're just going to stack them on top of one another. That's going to give me my system. Today it's going to be two equations stacked on top of one another. Tomorrow it's going to be three equations stacked on top of one another. And what I'm interested in doing on this is finding out what x and y can be such that it satisfies both equations. Okay, so I can come out three ways. I can have my answers be independent, meaning that if I graph my first linear equation, which is a line, and I graph my second one, which is a line, just making up two lines right now, wherever they cross right there, that is my XY answer. That is my one spot where they cross. So that's going to be my solutions, is where these lines cross. Well, if it's inconsistent, it has no solution. How do I make it so two straight lines have no solution? How do I make it so two straight lines do not cross? Parallel lines. So I'm going to have an inconsistent system whenever my lines do not cross, meaning that they will have the same slope, but a different y-intercept. Finally, a dependent solution. A dependent solution is going to be where it has infinitely many solutions. How do I draw two lines so that they intersect an infinite amount of times? Use red on this, find some space here. Draw the same line on top. Yeah. So it's going to be two lines that have the same slope and the same y-intercept. So these are the three types of answers that we will see. I'm going to start you off pretty easy, just checking a solution. I'm telling you that this one is independent, it has one answer, or maybe it has one answer, I don't know. I'm wondering if -2, 4 is where these two lines cross. Well, instead of graphing it, I can just use the idea that I have an x and a y together, and I can do the x and y, and I can plug those into both of these equations. So I'm going to work this top one off to the side. It's going to equal 2, hopefully. -6 plus 8 equals 2. Yeah, that worked. 2 equals 2. I'm good so far. I'm good so far. It has to work in both of them in order for this to be a go. So I need to take that -2 and I need to take the 4 and plug it into this one as well. I get -2 minus, thinking ahead, -2 minus 28 equals -30. -30 equals -30. Yes, that did work. If I get both of these to work, it's a yes. If either or both of them fail, it's going to be a no. So there's three different ways that we can actually solve these. I'm going to be interested in doing at least two of the three in this video. So solve the following system equations by graph. Okay, and let's identify the type of system, whether it crosses once, infinite amount of times, or not at all. So whenever I'm graphing, y equals mx plus b was my go-to in algebra 1 whenever I graph. So I got my slope, I got my y-intercept, boom, I can plug it in again. So I'm going to pull this one off the top right here, and I just need to subtract 2x off the other side. Plus 5. And I've got it in y equals mx plus b form. So however you learn to graph this, I always start with my y-intercept, 1, 2, 3, 4, 5, and go up to right here. That's 5. And then the -2. The -2, first of all, it's negative, so my slope's going to go up to the left. and the 2 is rise over run. So I'm going to rise 2, run 1. Or you may drop 2, run 1. As long as that line is going up to the left. Now from here, be careful, because my line is going to be where these cross at. Okay, so get a ruler out, go as straight as possible. I'll tell you, my blue line is not real good, but I think it will work. I want you to hit pause on the video. I want you to do the same thing that I did with the second equation down here. I want you to go ahead and solve it into y equals mx plus b, and plot it, and then we'll talk about where the answer is. Okay, hopefully you ended up with a line right here. If not, pause the video again and see how I got here. If you did get this line, then I am super interested in this point right here, where they cross. They cross at the point 2, 1, which is my answer. Since they only cross one time, we call this independent. However, you can see this. Okay. Well, there's easier ways to solve this. Graphing this and converting to y equals mx plus b each time, and then I'm only able to estimate about where it is. What if it came out to be a fraction? How am I supposed to find it there? Well, I can use something called the substitution method. So like always, I have the substitution method spelled out right here, just in Mr. Lovelady terms on this. What I'm going to do is I'm going to look at both equations, and I'm going to find a variable in both equations that I want to solve for. It doesn't matter if it's x or y. It doesn't matter if it's on top or bottom. I can just solve for one variable. Once I get that one variable solved for, I'm going to jump to the other equation and do a direct substitution in for that variable that I solved for. From here, I do a back substitution. I'll explain what that is in just a minute. And then you can always check your answer, just as we just did on example 1. On example 1. Just take the point that you found, plug it in for x and y on both equations. If you get both of them to be true, you're good. So I'm going to solve this by substitution. And whenever I solve this by substitution, what I'm going to be looking for is I'm going to be looking for a variable hanging out by itself. A variable that has a coefficient of 1. Because solving for that is going to be so easy. Y equals, I'm just going to subtract 2x off both sides. So it's very similar to how I was graphing it. Like I said, it doesn't have to be y every time. You might solve for x. Doesn't matter where it's at. So what I'm going to do now is I'm going to take this negative 2x plus 5, and I'm going to plug it into the variable that I solved for. So it's got to go into this y. And now I have something that looks like what we did the very first day in class. Whenever I had to solve a linear equation. Now, it makes me a little bit nervous getting fractions on some of these answers. I try to avoid that in the homework if I can in the quizzes. I think it's good that we see this because it kind of gives us an idea as to why we want to have a different system. So if I divide both sides by 16, I get 9 over 8. 9/8 would have been hard to find if I was just graphing this. I might accidentally just call it 1 instead of 9/8. Now here's where you're going to see me say back substitute. So I'm going to go back to some previous work that I've done. It's y equals negative 2 times x. And instead of x, I'm going to put in 9/8 plus 5. So I get negative 18 over 8 plus 5. I'm going to call it negative 9/4. I might change that 5 to 20 over 4. That'll make it easier to work with. I know some of your calculators do that. Kudos to you. But 9/8, 11/4. That number would have been very hard to get by graphing. Okay? You'd have to be pretty stinking precise on it. There's another method. I actually like this method a little bit better than substitution. I use both, but it's called the addition method. You will also hear me call it the elimination method. That will be a slip if that happens. But a lot of books do call it the elimination method. I'm trying to call it what I saw in your homework, and I called it addition method. What I'm going to do is I want to make sure both equations are in standard form, meaning x and y are on one side, and then the numbers normally on the right side of the constant. And what I'm going to do is I'm going to look at my constants, look at my coefficients in front of my x and my y, and I want to try to get one of my variables to cancel. So they might already line up and cancel. I might multiply one equation by something and it cancels, but I want to use multiplication to multiply in a whole equation to make it so one of the variables cancel. Whenever I get one of the variables to cancel, I'll be left with something linear. I can just solve it. 4 is my, I'm going to call that back substitute. And that's just going to substitute the value into one of the original equations and solve the second variable. And number 5, you can always check your answer on this. Okay. So step by step, what I'm doing is right here. Let's have it make sense with some numbers. So looking at this one, I'm looking to cancel out a variable. Man, I got a stinking nice variable. It's already ready to be canceled. What I mean by canceling is that if I was to add these two up vertically, these would just cancel. 3y, take away 3y, 0. I'm left with 3x, and if I add these, I get negative 3. Oops, that's a positive. So x is negative 1. So yeah, substitution would not have been hard on this one, but look how much easier elimination was. Definitely could have used substitution and got the right answer though. I just want you to know that. So now here's where I back substitute. Now I don't have any previous work on this. So I'm going to back substitute into either one of these original equations. I'm going to choose the top one. Just because the numbers are smaller and the x is hanging out by itself. So when I plug a negative 1 into that x, I don't have to worry about multiplying it. Add 1 to both sides, which I already did in my head. Stuff gets me a little excited sometimes, I guess. Divide by 3, and I get my answer. If I was to graph these two straight lines, they would cross at the point negative 1, positive 2. Let's see if you can do this one. All right, you gotta multiply by something on this one and get it to work. Actually, let's do this one together. I'll turn you loose on the next one. Okay. So looking at this, I can multiply one or both equations by something in order to get the correct answer. I'm just looking at it. I like what one of my students said earlier. He said, well, I don't like this 8/3 right here. And just multiply by 3 makes this no fractions. I would take it a step further. I would multiply it by negative 3. Because if I multiply this by negative 3, that negative 3y is going to cancel with this positive 3y up here on the top. So if I multiply it by negative 3, I got to multiply everything by negative 3. So that's going to give me a negative 8 right there. Be careful. So now this equation is like dead to me now. I don't plan on coming back to it. If I need to, I'll erase that blue line and get back to it. But what I'm going to do is I'm going to add the top and the bottom here. So 9x minus 12x is negative 9x. 3y, negative 3y cancel. So negative 9. So my x came out to be 1. So if my x is 1, what I'm going to do now is I'm going to back substitute. Again, I've got to back substitute into one of these. If I mark that one out, I'm just going to back substitute into this top one right here. So 3 plus 3y equals negative 1. Keep pausing. It feels like I did something incorrect on this. We'll go with it. I don't see it off the top of my head. If you do see it, leave me a comment or something. I don't see it. I think I'm good. So I get the point 1/4. That's where these two lines cross. Kind of an obscure point again. Even tough to find. All right, I'm just checking myself on this. Anyway, I will turn you loose on this one. On this one, you're going to have to multiply both equations by something in order to get a variable to cancel. Now, I will say there's multiple things that you can multiply both of these equations by to get x or y to cancel. So you choose it. Maybe you work in a different way than what I'm going to work in. And we'll see if we still get the same answer. So go ahead and hit pause. Back to fractions on this one. I chose to make it so that my y's right here gave me 12. Someone earlier today multiplied the top one by 4 and this next one by 6 and got them to equal 24. Guess what? They got the same answer I just looked at the smallest thing they both go into to keep my numbers halfway same. This is what I did. Okay, so this is how I plan on asking you on your assessments in here how to solve. I'm just going to say solve however you want to. So I'm just going to hit pause again. You solve this however you want to. Okay. You might have done the same thing, but I solved it both ways. In both ways, I get my x's and y's to leave the equation. And I'm left with a statement that is not true. 0 does not equal 1 if I tried to do addition method on this. 2 is not equal to 3 if I tried to do the substitution method. And so what does that mean? Anytime that happened earlier in the year, we just call it no solution. And that's exactly what we're going to call it again today. No solution, meaning that if I was to graph both of these lines, I would end up with parallel lines that never cross. So that hopefully makes sense to you. Let me work this one together. If it changes, there it goes. I might teach this a little bit different than your previous teacher might have done. But I'm looking at this, it's a y by itself. Yeah, substitution wouldn't be too bad, but a negative 1. I'm going to end up dividing everything by -1. Instead of doing that, I'm just going to go ahead and multiply this top one by a -3. Okay, so it's going to give me -9x plus 3y equal to -21. Either way I work it, whether I do addition like I did here, or substitution, I'm going to end up with 0 equals 0, or at least two things that are equal to each other. So that's just the opposite of no solution, which would be infinitely many solutions. Now I want to take this one step further. It is infinitely many solutions, but I want you to tell me what x and y could be. Now x could be anything. Since we're not pinning down a single point, let's just let x be anything. And to find out what y is, if you work this using substitution, I'm just going to go ahead and add y to the other side. 3x equals y plus 7, and then subtract 7. 3x minus 7 equals y. A couple ways you could have got there. And this is what y would be. Y in terms of x would be 3x minus 7. So while it can be any solution that you think of, whatever I want to plug in for x. Suppose I want to plug in 10 in for x right here. 10 and then the point 3 times 10 minus 7, 23 would also be on this line. So the point 10, 23 works. The point 9, 20 works. So there's infinitely many solutions. I do want to see this last step when you get down to this right here. And all this 3x minus 7 is simply the equation of y. Word problem. I'll help you set this one up, and then I'm going to let you solve it to keep the video hopefully under 20 minutes. That's my goal. Movie tickets to Santa Claus Conquers the Martians. We're in the Christmas season now, so I thought this was a pretty good movie. I've actually never seen it. But in order to get into this movie, it costs $9 for adults and $7 for children. So on a day where 325 people paid an admission, the total receipts that they pulled in were $2,495. Using this information, I want to know how many people that paid were adults and how many were children. Now, I think the easiest equation to get from this, if I just let my adults be my A and my children be my C, so instead of using X and Y, I'm going to use A and C, is that if I take the total number of adults plus the total number of children, it equals the 325 people that came out. That one might be the harder equation for you. I don't know. I asked this earlier, and I was given the other equation first. They told me that for every adult that came in, they had to pay $9, but for every child that came in, they had to pay $7. And whenever they did that, the total receipts that day were $2,495. So here's my two equations. I'm going to let you go ahead and solve this, and then I'll have the answers up on the slide. So then hit pause. Make sure somehow at the end of the problem you let me know that your adults, there were 110, and your children, there were 215. And so if you want to use A and C, if you kept X and Y, please make sure you either label your numbers 110 adults, 215 children, or if you just use A and C, I will be able to piece that together to know, so that I know that you know